There is a photograph. It sits inside a data file on a server at the Space Telescope Science Institute in Baltimore, Maryland, and it looks, at first glance, like almost nothing at all. A handful of pixels, a smudge of reddish light so small and so faint that were you to print it on a sheet of paper, it would barely be visible at the tip of a ballpoint pen. You could hold it between your fingers, you could sneeze and lose it, and yet that smudge is the most distant object any human being has ever seen. It is a galaxy, a real, living, burning, star-forming galaxy, with a mass somewhere in the range of 100 million times the mass of our Sun. It existed, it blazed, it built stars out of hydrogen in a fury of creation that, on any ordinary scale, would be unimaginable. And it did all of this just 280 million years after the Big Bang, at a moment so early in the life of the universe that by all rights it should not have been there at all. The galaxy is called MOM-Z14. It was discovered in May 2025 by an astronomer named Rohan Naidu and 45 colleagues who had set out specifically to answer a question that had been gnawing at cosmology since 2022. Are the galaxies James Webb keeps finding in the early universe a mirage or a miracle? The answer, it turns out, is miracle. But what that miracle means is more unsettling than the question itself. How does a galaxy form this fast? How does it produce oxygen? A heavy element that requires dead stars to create, in a universe so young that multiple generations of stars should barely have had time to live and die. And if the universe can produce structures like this at redshift 14, what else is out there that we have not yet seen, lurking at the very edge of everything, waiting for a telescope brave enough to look? Those are the questions, and none of them have clean answers, not yet. To understand why a single smudge of reddish pixels in a data file shook the foundations of modern cosmology, you first have to understand the machine that captured it, what it cost to build, why it almost never flew, and what the universe looks like when you see it through an eye that never existed before in human history. The James Webb Space Telescope is, by almost any measure, the most complex scientific instrument ever built. Its primary mirror spans 6.5 meters from edge to edge, a polished gold-coated surface made from 18 hexagonal segments of beryllium, a metal chosen because it is both light enough to launch and stiff enough to hold its shape at the extraordinary cold of deep space, roughly 233 degrees below 0 Celsius. Each of those 18 mirror segments weighs approximately 20 kilograms. Each is coated in a layer of pure gold just 700 atoms thick, because gold reflects infrared light with an efficiency that no other commercially viable material can match. The total polished area of the primary mirror is 26, 3 square meters. Hubble's was 4.5 square meters. When Webb looks at the sky, it collects more than 5 times as much light as Hubble ever could, and it does so at wavelengths of light that Hubble was essentially blind to. That last point matters enormously, and it is worth sitting with for a moment before moving on. Hubble was primarily an optical and ultraviolet telescope. It saw the universe roughly as our own eyes would see it, if our eyes were impossibly sensitive and positioned above the atmosphere. Webb, by contrast, is an infrared telescope. It detects heat radiation, long-wavelength light, the kind of glow emitted by objects that are too cool to shine brightly in visible light, or whose visible light has been stretched by the expansion of the universe into the infrared end of the spectrum. And this distinction, this single technical choice about what kind of light to observe, is the reason Webb can do something Hubble could not. It can look back toward the beginning. The universe is expanding. It has been expanding since the moment of the Big Bang, 13.8 billion years ago, and as it expands, it stretches the light that travels through it. Think of it this way. Imagine drawing a sine wave on a rubber band. Now stretch the rubber band. The wave gets longer. Its peaks spread further apart. The frequency drops. What was once ultraviolet becomes visible. What was once visible becomes infrared. What was once infrared becomes microwave. The further away a galaxy is, and therefore the longer its light has been travelling through expanding space, the more that light has been stretched, redshifted in the language of astronomers. and the further it has been pushed down the electromagnetic spectrum, away from visible wavelengths and into the infrared. This is what a redshift number actually means. When astronomers say MOMZ 14 has a redshift of 14.44, they are saying that the light we receive from that galaxy today has been stretched to 15.4 times its original wavelength, or, to put it in physical terms, that we are seeing the galaxy as it existed when the universe was just 280 million years old, at a point when the observable cosmos was so much smaller and denser and hotter that it barely resembles the universe we inhabit today. The light from that galaxy has been travelling through expanding space for roughly 13.53 billion years. It left its source before the Earth existed, before the Sun existed, before the Milky Way had fully assembled itself, before almost anything we would recognise as a galaxy had settled into the graceful spiral and elliptical shapes that populate the modern universe. Hubble could not see this far. The infrared detectors it would have needed either did not exist in sufficient sensitivity or could not be cooled sufficiently in the near-Earth environment where Hubble orbits. Webb was designed specifically for this task, and to do it, the engineers at NASA and the European Space Agency and the Canadian Space Agency chose to position it at a point in space called the second Lagrange point, or L2, about 5 million kilometers from Earth in the direction directly away from the Sun. At L2, Webb sits in a gravitational sweet spot where it orbits the Sun in lockstep with the Earth, always facing away from both the Sun and our planet, shielded from their heat and light by a 5-layer sunshield the size of a tennis court, a gossamer structure of Kapton foil, each layer thinner than a human hair, designed to keep the telescope's instruments at a temperature where thermal noise does not overwhelm the whisper of infrared light arriving from 13 billion light-years away. And then there is the cost, $9.7 billion. 24 years from initial concept to first light. 7 major delays, each one prompting congressional hearings and budget reviews, and serious discussions about cancellation. In 2011, a House Appropriations Subcommittee actually voted to terminate the project, citing cost overruns that had ballooned the original budget by a factor of roughly 20. The telescope was saved by a coalition of scientists, engineers, and advocates who argued, with a passion that bordered on desperation, that no other instrument could do what Webb was designed to do. They were right. They were more right than even they understood at the time. Webb launched on Christmas Day 2021 atop an Ariane 5 rocket from the Guiana Space Center in Kourou, French Guiana. The launch was, by every measure, a success, and it needed to be because Webb was not serviceable. Unlike Hubble, which was designed to be visited by astronauts who could replace components and fix problems in orbit, Webb sits too far from Earth for any crewed mission to reach it with current technology. It had one chance to work, and it had to unfold itself autonomously after launch, deploying the sunshield and unfolding the mirror in a sequence of 344 single-point failures, 344 moments where, if a single hinge did not release or a single actuator did not fire, the most expensive scientific instrument in history would have become the most expensive piece of space debris in history. It worked. Everything worked. Every single mechanism deployed correctly. And in early 2022, Webb cooled down to operating temperature, aligned its 18 mirror segments to a precision of 150 nanometers, roughly 1/600th of the width of a human hair, and began to see the universe in a way it had never been seen before. The first full-colour science image was released on July 12, 2022. It showed a patch of sky near the constellation Volans, containing a cluster of galaxies called SMACS 0723. The cluster acts as a gravitational lens, bending and magnifying the light of more distant galaxies behind it, and the image revealed hundreds of those distant galaxies in extraordinary detail. Swirls and arcs of light, billions of light-years away, each one a full galaxy containing hundreds of billions of stars, all of them visible in a patch of sky so small that you could cover it with a grain of sand held at arm's length, Scientists who had spent decades building, advocating for, and waiting for Webb looked at that image and wept. Not from sentimentality, but from the sheer recognition that everything they had promised this machine could do, it was doing in the first 12 hours of operation. But that was only the beginning, because among the galaxies revealed in Webb's earliest deep field images were ones that should not have been there. Galaxies that were, by the best available theories of cosmological structure formation, impossible. Galaxies that were far too large, far too bright, far too chemically complex, forming far too early in the history of the universe for any standard model to account for. And the deeper Webb looked, and the farther back in time its extraordinary infrared eye peered, the worse the problem became. This is where our story properly begins. The question is not just how far can we see? The question, the one that keeps astrophysicists awake, is why does what we see not match what we expected? And the answer to that question, when it finally comes into focus, does not merely refine our understanding of early galaxies. It challenges the story we tell about the universe itself. Before Webb flew, cosmologists had a model. It was a good model, tested, refined and cross-validated against decades of observations from radio telescopes, optical surveys, the cosmic microwave background and the Hubble Space Telescope. It was called Lambda CDM, or the Lambda Cold Dark Matter Model, and it described with extraordinary precision the large-scale structure of the universe, how it expanded after the Big Bang, how dark matter clumped together under gravity, how those dark matter clumps, called halos, grew over time and attracted the ordinary matter that eventually cooled, condensed, and ignited into stars. The model made specific predictions. In the first few 100 million years after the Big Bang, those dark matter halos would be small. They had not had time to grow. They contained relatively little mass, and therefore the galaxies that formed inside them would also be relatively small and dim. The universe at redshift 10, 12, 14 was expected to be a sparse, dark place, a cosmic nursery of tiny, fragile proto-galaxies barely distinguishable from the background noise, faint enough that even Webb would struggle to detect them, and would require dozens of hours of exposure time to confirm even one or two. This prediction was not a guess. It was the output of some of the most sophisticated computer simulations ever run on Earth. Simulations that tracked the gravitational interactions of billions of dark matter particles across cosmic time, embedded ordinary matter into the resulting halos, and modelled the physics of gas cooling, star formation, stellar feedback, and chemical enrichment with painstaking care. These simulations had been validated against the observed galaxy population at lower redshifts. They worked beautifully for the universe we could already see. And then Webb turned on, within weeks of first light. Weeks, not months, not years, astronomers began reporting something extraordinary. The early universe was not dark and sparse. It was bright. It was by some measures outrageously, preposterously bright. Photometric survey after photometric survey, meaning surveys that estimated the distances of galaxies from the colours of their light rather than from detailed spectra, kept identifying objects at redshifts of 10, 11, 12 and beyond, objects that were not only present but luminous, in some cases more luminous than almost any galaxy in the modern universe. The initial reaction in the community was caution. Photometric redshifts are not always reliable. A galaxy at redshift 2 with unusual colour characteristics can sometimes mimic a galaxy at redshift 12 in a photometric survey, and the history of observational cosmology is littered with high redshift candidates that turned out, upon closer spectroscopic scrutiny, to be perfectly ordinary nearby galaxies wearing unusual disguises. The correct scientific response was to withhold judgment until spectra were obtained. The spectra came, and instead of explaining away the excess of bright early galaxies, the spectra confirmed it. Galaxy after galaxy, confirmed spectroscopically at redshifts between 10 and 14, turned out to be not only real but more massive, more luminous and more chemically enriched than anyone had any right to expect. By mid-2022, a galaxy called JADES GSZ 130 had been confirmed at a redshift of 1320, meaning we were seeing it as it appeared just 400 million years after the Big Bang, and it was already clearly visible, clearly extended, clearly a real structure with real stars. By early 2024, that record had been shattered by a galaxy called Jedda's GSZ 14-0, confirmed at a redshift of 1432, placing its formation at just 290 million years after the Big Bang. And then by May 2025, that record was shattered again by MOMZ-14, confirmed at redshift 1444, 280 million years after the Big Bang, 100 times more common in that narrow slice of early cosmic history than any pre-Webb model had predicted. Let me put that number in context, because 100 times more common does not fully convey the weight of what it means. When Rohan Naidu and his colleagues designed their Mirage or Miracle survey, named for precisely the question it was designed to answer, they calculated that the survey area of approximately 350 square arc-minutes should, based on pre-Webb consensus models, turn up essentially 0 spectroscopically confirmed galaxies at redshifts between 14 and 15. The models were clear on this. The halos at that epoch were too small, the universe too young, the density of bright sources too low. They might find one perhaps if they were extraordinarily lucky. A statistical outlier, a fluke. Instead, they found MOZ-14, and the number density it implies is more than 182 times higher than the models predicted. The uncertainty on that factor is large. It could be as low as 77 times higher, or as high as 511 times higher. But even at the lower bound, even with every source of statistical uncertainty applied in the most conservative possible direction, the density of bright galaxies at redshift 14 to 15 is incompatible with the pre-Webb standard model of galaxy formation. This is what scientists sometimes call a 10 sigma result. Not in the strict statistical sense, but in the rhetorical sense that the discrepancy between observation and expectation is not a rounding error, not an instrumental artifact, not a calibration mistake. It is a real, robust, reproducible disagreement between what we see and what we predicted we would see, and it demands an explanation. But there are 3 things about these early galaxies that make the problem even harder to dismiss, even harder to paper over with minor adjustments to existing models. And the third one, discovered by a team using a radio telescope array perched 5, all 58 meters above sea level in the Atacama Desert of northern Chile, is the one that to my mind rewrites the problem entirely. First, the sizes. Jedda's GSZ 14-0 spans roughly 1,600 light-years across. That is not enormous by modern standards. The Milky Way is about 100,000 light-years in diameter, but for a galaxy that existed just 290 million years after the Big Bang, it is extraordinary. It is far larger than theoretical models predicted for a galaxy at that epoch. It is not a compact knot of a few hundred newly born stars. It is an extended structure, already spatially resolved, already distributing its light across a physical scale that implies substantial gravitational assembly. To be 1/600 light-years across at redshift 14, that galaxy had to have been growing rapidly, continuously, voraciously from an even earlier time, second the luminosity. Jade's GSZ 14-0 has an ultraviolet absolute magnitude of 20.81. MOMZ-14 has one of 20.2. These are not faint objects scraping against the detection threshold of the most powerful telescope ever built. These are genuinely bright galaxies, pumping out ultraviolet radiation at a rate comparable to luminous galaxies in the modern universe, and the primary source of that ultraviolet light, in the Jedda's GSZ 14-0 case, can be established with some confidence. It is mostly young stars. The spatial extent of the emission rules out a single compact quasar or active galactic nucleus as the dominant light source. This galaxy is forming stars at a rate that, scaled to its tiny mass, is extraordinary by any measure. Third, the oxygen, and this is the one that changes everything. Oxygen is not a primordial element. This point is worth stating clearly, because it carries consequences that ripple backward through the entire logic of early universe formation. When the Big Bang happened, when the universe burst into existence in a state of unimaginable heat and density, and began to expand and cool. The physics of nuclear reactions in those first few minutes produced a specific set of elements in specific proportions, roughly 75% hydrogen, roughly 25% helium, trace amounts of lithium and beryllium, and that was it. Everything else, carbon, oxygen, nitrogen, iron, calcium, silicon, every element on the periodic table beyond beryllium did not exist. It could not exist, because the conditions for making heavier elements through nuclear fusion, the crushing temperatures and pressures at the cores of stars, had not yet formed anywhere in the universe. The first stars that lit up after the Big Bang, what astronomers call population 3 stars, were made almost entirely of hydrogen and helium. They were giants by modern standards, because without heavier elements to cool the gas clouds from which they formed, those clouds could not fragment efficiently into small, compact objects, and instead tended to collapse into extraordinarily massive balls of gas, potentially hundreds of times the mass of our Sun, burning brilliantly and briefly before dying in spectacular supernovae that seeded the surrounding space with the first heavy elements those stellar furnaces had synthesized. This is the process by which oxygen enters the universe. Stars fuse hydrogen into helium, helium into carbon, carbon into oxygen, and so on up the chain of nuclear reactions, building progressively heavier elements in their cores over their lifetimes. When a massive star exhausts its fuel and explodes as a supernova, it scatters those synthesized elements, including oxygen, into the surrounding interstellar medium. The next generation of stars forms from gas already enriched with these heavy elements. The process repeats. With each stellar generation, the chemical complexity of the universe increases. This process takes time. It takes multiple stellar lifetimes, even the most massive stars, the ones that live fast and die young in supernova explosions after just a few million years, need those few million years, and for a galaxy to accumulate enough oxygen to be detectable at the level observed in JDES GSE 14-0, you need not one generation of massive stars, but multiple. The cycle of stellar birth, nuclear fusion, and explosive death needs to have run its course not once, but several times. Several generations of stars need to have lived and died within the first 290 million years of the universe's existence. Let that sink in. In a universe that was just 290 million years old, a galaxy had already run through multiple full cycles of star formation and stellar death, accumulated 10 times more heavy elements than any model predicted should exist at that epoch, and was broadcasting the signature of those elements, specifically the emission line of doubly ionized oxygen, the OV88 micron line, clearly enough for ALMA's array of 66 radio antennas spread across the high Atacama Plateau to detect it from 13.4 billion light-years away. I was astonished by the unexpected results, said Stefano Carniani of the Scuola Normale Superiore in Pisa, lead author of the ALMA detection paper. The evidence that a galaxy is already mature in the infant universe raises questions about when and how galaxies formed. This is, in the polished language of scientific understatement, a considerable observation. What Carniani is actually saying is, this should not be here, not because there is anything physically impossible about it in principle. The universe is not required to obey our models, but because our models, built on decades of careful, theoretically grounded work, confidently predicted that it would not be here, and it is, with oxygen. 10 times more oxygen than expected. Sander Schaus, a PhD candidate at Leiden Observatory whose team independently confirmed the oxygen detection, offered perhaps the most vivid encapsulation of the surprise. It is like finding an adolescent where you would only expect babies. Think about what that metaphor implies. You set up a telescope expecting to photograph a maternity ward. Instead, you find a 16-year-old who has already learned 3 languages, built a company, and published research. The question is not, is this person real? They are standing right in front of you. The question is, where did the time come from? And that question, where did the time come from, is the one that opens into the deepest, most consequential territory in modern cosmology. There are, broadly speaking, 4 ways to resolve the tension between what Webb sees and what lambda CDM predicts. Each one has strengths and weaknesses, and none of them is yet fully satisfying. But taken together, they sketch a picture of early cosmic history that is substantially more chaotic, more efficient, more extreme, and more strange than the picture that prevailed before December 2021. The first resolution is the simplest and also the least exciting. Perhaps the models of star formation efficiency are wrong. In the standard lambda CDM picture, only a modest fraction of the gas that falls into a dark matter halo actually ends up converted into stars, typically somewhere between 10 and 30%. Depending on the specific conditions, the rest is expelled by stellar feedback, supernovae, radiation pressure, and the powerful winds blown by massive stars as they age. If, in the early universe, those feedback mechanisms were less effective. If early galaxies were simply better at turning gas into stars than models assumed, then the galaxies could accumulate more stellar mass more quickly, and the luminosity problem largely goes away without requiring any new physics. You would just need the early universe to have been more efficient at making stars than we thought. This explanation has the attractive quality of being, in principle, testable. If early galaxies had higher star formation efficiencies, the signatures of that efficiency should be visible in other properties of the galaxy population. And indeed, some observational evidence does suggest that star formation in the early universe was more bursty and episodic than at later times, with galaxies going through intense bursts of star formation followed by periods of relative quiescence, rather than the steadier, more gradual star building that characterizes most modern galaxies. Bursty star formation can make a galaxy temporarily much brighter than its average stellar mass would suggest, which could at least partly explain why so many early galaxies appear more luminous than expected. But the star formation efficiency explanation runs into trouble when confronted with the most extreme cases. For JADES GSZ 14-0, with its implied stellar mass of several 100 million solar masses and its oxygen abundance 10 times above expectations, even an implausibly high star formation efficiency, far above anything observed in the modern universe, struggles to explain the full picture. You need not just to form stars fast, but to form them, watch them die, collect the oxygen they produce, form more stars from the enriched gas, watch those die too, and then form still more stars, all within a window of less than 290 million years. At some point, the efficiency argument stops being a modest correction to existing models and starts being a demand for a completely different physical regime. The second resolution is more radical. Perhaps the initial mass function of stars in the early universe was different. The initial mass function, the IMF, is the statistical distribution of stellar masses when a batch of stars forms from a gas cloud. In the modern universe, it follows a relatively well-characterized pattern, with most stars being small and cool, and only a minority being large and hot and short-lived. If the early universe preferentially formed massive stars, big, hot, short-lived objects that lived and died quickly, producing large amounts of heavy elements per unit of time, then the chemical enrichment problem becomes significantly easier to solve. More massive stars per unit of stellar mass means more supernova explosions per unit of time, more oxygen produced per unit of total stellar mass, and a chemical enrichment rate that could, in principle, explain the oxygen abundance in JADES GSZ 14-0 without requiring an absurd number of stellar generations, and there is good theoretical reason to think that the initial mass function in the early universe was indeed different. Population 3 stars, the first generation, forming from pristine hydrogen and helium, were expected to be enormously massive, and some simulations suggest they could reach masses of 100 to 1,000 solar masses or more. As the gas from which subsequent stellar generations formed became enriched with heavy elements, the cooling properties of that gas changed, allowing it to fragment into smaller clumps and form more ordinary lower mass stars. So the shift from a top-heavy IMF, dominated by massive stars, to the more ordinary IMF of today may itself be a transition that played out in the early universe, with the first few 100 million years hosting a stellar population dramatically more massive and more short-lived than anything that exists today. If this is correct, and it remains a hypothesis, not an established fact, it would help explain both the brightness and the chemical enrichment of early galaxies simultaneously. Massive stars shine brilliantly, boosting the ultraviolet luminosity of young galaxies far above what the same total stellar mass would produce from ordinary stars. And massive stars die prolifically in supernovae, distributing oxygen and other heavy elements into the surrounding gas far faster than lower mass stars can. The third resolution involves the nature of dark matter itself. The Lambda CDM model is built on a specific model of dark matter, cold dark matter, meaning dark matter particles that move slowly compared to the speed of light and therefore clump effectively on small scales, forming the dense halos inside which the first galaxies assembled. If dark matter were actually warmer, if the particles moved faster and therefore smeared out the density fluctuations on small scales, then the formation of small, compact halos in the early universe would be suppressed, and the first luminous structures would form differently. Some models of warm dark matter, or of dark matter with self-interactions, predict a somewhat different distribution of early halos that might, in certain parameter regimes, allow for the formation of more massive early galaxies in some regions, while predicting fewer galaxies overall. This explanation is more speculative, and the evidence for any modification to the standard dark matter model from the JWST observations alone is contested. But it cannot be ruled out, and it points toward a broader truth. The JWST discoveries are not just a puzzle for galaxy formation physics, they are a probe of the fundamental nature of dark matter itself. The invisible substance that makes up roughly 27% of the energy density of the universe, the scaffolding on which every structure we have ever observed is built. The fourth resolution is the most dramatic, and also the most hotly debated. Perhaps the early universe contained a population of primordial black holes. Black holes formed not from stellar collapse, but directly from density fluctuations in the first seconds of the universe. And perhaps these primordial black holes acted as the seeds around which matter could accumulate with extraordinary efficiency, accelerating the formation of massive dark matter halos, and within them massive galaxies. This idea has a long history in cosmology, having been proposed in various forms for decades, but the JWST discoveries have given it new urgency. If the density of bright early galaxies implied by MOMZ14 and its cousins is truly 100 to 200 times higher than standard models predict, then some mechanism for fast-tracking structure formation in the very early universe is almost certainly required. And primordial black holes are among the most natural candidates. Here is what keeps this problem honest, though, and why the answer is not yet clear. All four of these explanations, higher star formation efficiency, a top-heavy initial mass function, modified dark matter, and primordial black holes, can be made to work quantitatively in isolation. The trouble is making them work together consistently across the full range of observed properties of early galaxies. JADE's GSZ14-0 is not just bright and massive and oxygen-rich. It is also extended, spatially resolved, dusty despite being so young, and already showing the spectroscopic signatures of ionized gas. MOMZ14 is compact, almost dust-free, with a stellar population that appears to have experienced a tenfold increase in star formation rate in just the last 5 million years of its observed existence. These are not the properties of a single, unified class of object. They are the properties of a population of galaxies that formed in a variety of ways, under conditions that defy any single clean explanation. And there is one more fact about MOMZ14 that does not fit neatly into any of the four resolutions above. It is a detail buried in the spectroscopic data, in a few faint emission lines detected at only a 3 sigma significance, but it is the detail that Rohan Naidu and his co-authors flagged as perhaps the most intriguing aspect of their discovery. Z14 shows a chemical abundance pattern, a ratio of nitrogen to carbon in its gas, that is not just unusual, it is a pattern previously observed in only one class of objects in the entire modern universe. and those objects are not galaxies. They are globular clusters. A globular cluster is one of the most ancient and beautiful structures in the universe. It is a tightly packed ball of stars, typically between 100, 0 and a few million stars, orbiting the outskirts of a large galaxy like the Milky Way, bound together by mutual gravity into a sphere only a few hundred light-years across. The Milky Way contains about 150 of them. They are among the oldest objects we can directly study. Many globular clusters are 12 to 13 billion years old, meaning they formed within the first billion years of the universe's existence, preserving in their stars the chemical signatures of an extraordinarily early epoch in cosmic history. And here is what makes them peculiar. The stars within individual globular clusters show anomalous chemical abundance patterns, specifically enhanced nitrogen relative to carbon and oxygen in a configuration that does not match any ordinary stellar nucleosynthesis model. This anomaly has been one of the great unsolved problems in stellar astrophysics for decades. It implies that globular cluster stars formed from gas that had already been processed through an unusual source of chemical enrichment, something that produced large amounts of nitrogen relative to other elements, something that ran through multiple cycles of nuclear processing quickly enough to enrich the gas before the cluster stars formed. The leading candidate for that unusual source is supermassive stars, objects not 100 or even 1,000 solar masses, but potentially 10,000 solar masses or more, objects so massive that they lie at the very edge of what the laws of physics permit, burning through hydrogen at an extraordinary rate in an extraordinarily short lifetime, processing enormous quantities of gas through a distinctive nucleosynthetic pathway that naturally produces enhanced nitrogen relative to carbon. These supermassive stars are theoretical. No one has directly confirmed their existence. But their predicted chemical signatures match the anomalous abundances seen in globular clusters across the Milky Way, in other galaxies, and now, if the emission lines in MOMZ-14's spectrum are real, in the most distant galaxy ever confirmed by spectroscopy. MOMZ-14 has supersolar nitrogen to carbon ratios. The NC ratio in its emission lines is greater than 1 in solar units, a level seen in the modern universe only in the most ancient globular clusters and in a handful of high redshift galaxies observed by Webb. And the interpretation offered by Naidu and his team is, to my mind, one of the most remarkable ideas to emerge from JWST observations yet. We may be watching the formation of globular cluster stars in real time. If this interpretation is correct, then MOMZ-14 is not just a distant galaxy. It is a snapshot of the moment when some of the oldest surviving stellar structures in the universe. The globular clusters that orbit galaxies like the Milky Way today, whose stars we can resolve individually with ground-based telescopes, whose chemistry we have been puzzling over for half a century, were being born. The stars forming inside MOMZ-14 at redshift 14. 44 may be the very stars that, 13.5 billion years later, comprise the globular clusters we see around us today. This is not a metaphor, it is a literal possibility. It would mean that when a radio astronomer in Santiago looks up at the Milky Way on a clear night and sees the globular cluster 47 Tucanae, a dense ball of 500,000 stars just 700 light-years from Earth, they are looking at objects whose formation they can now study directly at cosmic dawn, in the spectrum of a galaxy 13.53 billion light-years away, past and present, separated by almost the entire age of the universe, connected by a thread of chemistry preserved in the ratios of a few atomic emission lines. I find this connection genuinely haunting. It is one of those moments in science where two things that seem to belong to entirely separate domains of inquiry, the internal chemistry of ancient stellar clusters in the modern Milky Way and the spectroscopy of the most distant known galaxy in the universe, turn out to be reflections of the same underlying process, the same physical event, separated by 5 billion years of cosmic time, but united by the unchanging laws of nuclear physics. But the connection to globular clusters does more than create a poetic link across cosmic time. it raises a specific testable prediction. If the stars forming in MOMZ14 really are the progenitors of globular clusters, they should eventually settle into compact, gravitationally bound stellar systems with the characteristic chemical abundances of globular clusters. And conversely, if we could trace the globular clusters orbiting the Milky Way and other nearby galaxies back to their birthplaces, back to the high redshift galaxies where they formed, we would be following a thread of cosmic history that spans virtually the entire age of the universe. The implications extend outward from there. Because if globular clusters form in the very earliest galaxies, at redshifts of 1415, perhaps even higher, then they are not just old structures orbiting modern galaxies. They are relics of the epoch of cosmic dawn itself. They are fossils of the first era of structure formation, preserved by the extraordinary stability of gravitational binding, surviving for 5 billion years while everything around them, gas clouds, dark matter halos, the parent galaxies in which they formed, was disrupted again, merged and transformed beyond recognition. The stars in a globular cluster are, in a real sense, the oldest material objects in the accessible universe that we can examine up close, and we are now watching them form. There is, however, a complication to the globular cluster interpretation of MOMZ14, and it is the kind of complication that reveals just how many layers of uncertainty are stacked beneath even the most compelling discoveries. The nitrogen-to-carbon ratio in MOMZ14's spectrum is measured at only 3 sigma significance, not the 5 sigma threshold conventionally required to claim a definitive detection in physics. The emission lines from which the ratio is derived are faint. They are at the edge of what the telescope's spectroscopic capability can reliably extract from a source this distant and this compact. More observing time, or photons, a more sensitive spectrograph configuration, any of these could sharpen the measurement and either confirm or refute the globular cluster interpretation. This is not a failure of the science. It is science working exactly as it should. A 3 sigma hint is a direction to look, not a conclusion to draw. The interpretation is plausible, well motivated, and consistent with the data, but it is not yet established, and anyone who tells you otherwise is outrunning the evidence. What is established, what the data confirm beyond reasonable doubt, is that MOMZ14 exists at redshift 14.44, that its light left 280 million years after the Big Bang, that it is luminous and compact and dust-free, and forming stars at a rate 10 times higher than its average over the preceding 50 million years, and that its number density in the early universe is more than 100 times higher than any pre-Webb model predicted. That is enough to demand a reckoning. That is enough to say, with confidence, that something about the way we understand the first hundreds of millions of years of cosmic history is wrong. Not trivially wrong, not slightly misspecified, but fundamentally incomplete in a way that the most powerful telescope humans have ever built is now exposing in exquisite, merciless, transformative detail. And the reckoning begins not in the abstract realm of theoretical cosmology, but in the very specific, very human story of the people who built the instruments, conceived the observations, spent years designing surveys, and then sat in front of their computer screens in the spring of 2024, and again in the spring of 2025, watching spectra appear on their screens that told them, unambiguously, that the universe had done something unexpected. Science, in its published form, appears clean. A paper arrives in a journal. It lists authors, states methods, reports results. It is impersonal in its syntax, declarative in its conclusions, stripped of the hesitation and confusion and excitement and doubt that attended every step of its making. This is by design. The conventions of scientific writing are meant to separate the conclusions from the personalities, the facts from the feelings, the result from the story of how the result was found. But science is made by people. It is made by human beings who sleep badly the night before a result comes in, who disagree furiously over interpretations at 6 a.m. before conferences, who have spent 5 years of their careers on a particular model that the data are now, quietly but insistently, undermining, understanding the discoveries from the James Webb Space Telescope, really understanding them, in the way that touches something beyond the technical, requires knowing something about the people who made them. Stefano Carniani is an assistant professor at the Scuola Normale Superiore in Pisa, Italy, one of the most elite research universities in Europe, a place where the entrance exam has an acceptance rate of approximately 3%, where students eat and live and breathe in buildings that have housed centuries of scholarship. Carniani specializes in the evolution of galaxies and black holes across cosmic time. He is a member of the NIASPEC Guaranteed Time Observations team, meaning his access to Webb observing time was built into the telescope's operations plan from before launch, a reward for the years his group spent helping to develop and calibrate the instrument. He had been working on high redshift galaxy candidates since the earliest weeks of JWST operations. In 2023, his team identified a source in their JDES survey data that had all the photometric characteristics of a very high redshift galaxy, but also, troublingly, some properties that did not fit neatly. It was close to another galaxy. It was surprisingly bright. It might be a mirage. The team was cautious. They waited. They obtained additional imaging data in October 2023 in the JDES Origins field, one of the deepest patches of skyweb had yet observed, and the narrower filter imaging confirmed the high redshift hypothesis more strongly. In January 2024, NIRSPEC, the near-infrared spectrograph, observed JEDS GS14e for almost 10 hours. The data were processed. The spectrum appeared on screen. Kevin Hainline, a co-author of the discovery paper and an associate research professor at the Steward Observatory at the University of Arizona, recalled the moment. Seeing this spectrum was incredibly exciting for the whole team, given the mystery surrounding the source. But the word exciting is doing enormous work in that sentence. What the spectrum actually showed was something that nobody in the room had been certain they would ever see in their careers. An unambiguous Lyman break at a redshift of 1432, shattering the previous record by more than a full redshift unit, confirming that this galaxy existed when the universe was just 290 million years old. A Lyman break is the signature left in a galaxy's spectrum when the hot young stars inside it produce large quantities of ultraviolet photons that are then absorbed by neutral hydrogen, both in the galaxy itself and in the surrounding intergalactic medium. Below a specific wavelength, the Lyman limit, at 91.2 nanometers in the rest frame, the galaxy simply disappears, its light completely absorbed. Above that wavelength, the galaxy shines brightly. In an expanding universe, that sharp edge is redshifted to longer wavelengths, and the exact wavelength at which it appears tells you the redshift of the galaxy with remarkable precision. For JDES GSZ14-0, the break appeared at a wavelength of roughly 9 microns deep in the infrared, placing the galaxy at Z14.32 with an uncertainty of 0.08.0820. The spectrum was shared internally within the JDES team. There was, by all accounts, a period of checking and rechecking, not because anyone doubted what the data showed, but because the data showed something so consequential that getting it wrong was unthinkable. Every spectrum has the potential to be contaminated by noise, by stray light, by instrumental artifacts. The JDES team went through every possible alternative explanation. Could this be a low redshift galaxy with an unusual spectral break that mimicked a Lyman break at high redshift? Could there be an error in the wavelength calibration? Could gravitational lensing by the nearby companion galaxy have introduced some artifact? The answer to all of these questions was no. The spectrum was clean, the redshift was real, and what is more, Webb's mid-infrared instrument, MIRI, had independently detected the galaxy at longer wavelengths corresponding to rest frame visible light, with a brightness that implied the presence of strong emission lines from ionized hydrogen and, crucially, oxygen. This was the first hint, even before the ALMA confirmation a year later, that something chemically extraordinary was happening in this galaxy. The JADES discovery paper was submitted to Nature and was published in September 2024. The response from the community was immediate and intense, not skeptical. The data were simply too clean for skepticism to gain a foothold, but deeply engaged in the specific way that happens when a result arrives that everyone knows is going to change the questions they are trying to answer. In parallel, at observatories around the world, teams were already preparing follow-up observations. At ALMA, the Atacama Large Millimeter Submillimeter Array, whose 66 antennas are arrayed across the high Atacama Plateau in Chile, at an altitude where the air is so thin and dry that carbon dioxide narcosis is a genuine occupational hazard. Two independent teams had trained their instruments on JDS GSZ 14-0 to search for the emission line of doubly ionized oxygen at a rest frame wavelength of 88 micrometers. Sander Schaus's team at Leiden and Stefano Carniani's team at Pisa analysed the ALMA data independently, knowing each other was working on the same target. The detection came back clearly from both analyses. The 030 88 micron line was there, in the same place, at the same redshift, with the same intensity, independently confirmed by two separate teams, using the same data but different analysis pipelines. The measurement also refined the galaxy's redshift to a precision that dwarfs the S-spec measurement, 14.1793, with an uncertainty of just 0.005%. As one of the authors noted, that is analogous to being accurate within 5 centimeters over a distance of 1 kilometer. Carniani's reaction when he first saw the oxygen detection is recorded in the ALMA press release. I was astonished by the unexpected results because they opened a new view on the first phases of galaxy evolution. The formal language is measured, but the feeling underneath it, sitting in Pisa with the ALMA data on your screen, knowing that you are looking at a detection of oxygen in a galaxy that existed 290 million years after the Big Bang, must have been something far less containable. I want to try to convey what this moment means, not technically but humanly, because I think it is one of the genuine threshold moments of 21st century science. For the entirety of human existence on this planet, for every civilization that looked up at the night sky, every philosopher who wondered about the origins of matter, every astronomer who pointed a telescope at the heavens, every physicist who derived equations of cosmic expansion, the early universe was entirely invisible. We had its fingerprints in the cosmic microwave background. We had its echoes in the abundances of hydrogen and helium. We had its shadow in the distribution of galaxies in the modern universe. But we had never seen it directly. We had never looked at a galaxy as it existed in the first few 100 million years of cosmic history and said, here it is. Here is a real structure. Here are its properties. Here is its chemistry. Now we can. Now Stefano Carniani can look at a spectrum on his screen in Pisa and say, in a galaxy that existed 13.4 billion years ago, when the universe was 2% of its current age, there was oxygen, there were stars, there were stellar deaths, there was a chemical history already in progress. The universe was not waiting politely for us to tell it what it was allowed to do. For Rohan Naidu at MIT, 27 years old when the MOM survey was designed, part of a generation of astronomers who grew up with Webb as a promise and are now living with it as a reality. The discovery of MOM Z14 had a different flavour. The Mirage or Miracle survey was designed partly as a test of nerve. Were the bright early galaxies real, or were they an artefact of biased photometric selection? Were the number densities implied by isolated discoveries like JDIS GSZ 14-0 representative, or was that galaxy a 1 in a million outlier? The only way to know was to survey a large area systematically, follow the candidates spectroscopically without cherry-picking the most promising ones, and count what came back. The survey covered approximately 350 square arc-minutes across the cosmos and UDS legacy fields. It targeted luminous high redshift candidates selected by photometric redshift fitting from the combined imaging of multiple overlapping WST surveys. Each of the 5 NIA-spec pointings received 4 hours of integration in the prism mode, enough to detect a Lyman break and measure redshifts for even moderately faint sources, while being insufficient for detailed spectral characterization of very faint objects. One of the targets in the cosmos field, was a source that had been identified in photometric catalogues as a promising redshift 14 candidate. It was compact, it was luminous at near-infrared wavelengths, it was completely absent at wavelengths shorter than about 2 microns. The photometric redshift fitting strongly preferred a solution above redshift 14, but photometric redshifts at these extreme distances are difficult, and contamination by lower redshift objects with unusual spectral features was a real concern. On April 16, 2025, the Aniaspec mask containing this source was observed. The data were reduced using standard JWST reduction pipelines and the MSAX spectral extraction software, and on May 16, 2025, the analysis was complete and the result was clear: a sharp Lyman alpha break, 5 UV emission lines, a spectroscopic redshift of 14.4.02. The most distant galaxy ever confirmed. The paper they wrote about it was titled, with deliberate and appropriate drama, A Cosmic Miracle. This is not hyperbole. The title reflects a genuine statistical argument. The probability that a single JWST survey of 350 square arc minutes would turn up a spectroscopically confirmed galaxy at redshift 1415 under the pre-Webb standard model of galaxy formation was essentially zero. The fact that it did is not a miracle in the supernatural sense. It is a miracle in the scientific sense. An event so improbable under the existing theory that it serves as compelling, arguably decisive, evidence that the existing theory is wrong. The survey's name, Mirage or Miracle, was chosen before the results were in. It was chosen as an honest acknowledgement that the bright early galaxies might be an observational illusion, a systematic error in photometric selection propagating through the data and creating the appearance of a population that did not really exist. The spectroscopic confirmation of MOMZ14, combined with the number density it implies, answered the survey's own question. It was not a mirage. What it was, what it means for the story of how the universe began its visible chapter, is something that cosmologists are still working out, and the human stories embedded in that working out are as varied, as personal, and as consequential as the story of any generation of scientists suddenly handed a window onto something they spent their entire careers hoping to see. There is the graduate student in Chile, who stayed up through 2 consecutive nights of ALMA observation, watching the noise statistics for the oxygen line, knowing that the moment the signal crossed the detection threshold, it would be the first confirmed detection of that element in the early universe. There are the theorists, not named in the discovery papers, but reading them with mounting urgency, who built the models that the observations are now contradicting, who must now decide how much of their framework to keep and how much to discard, a process that is intellectually difficult and personally costly in ways that the clean language of published papers never reveals. There is Carniani, writing in the acknowledgements of his ALMA paper that the work was supported by the European Research Council, a phrase that contains within it years of grant applications, referee reports, budget negotiations, and the slow, grinding bureaucratic machinery by which science gets funded and eventually gets done. And there is, perhaps, the most haunting human element of all: the scientists who spent their careers working on the JWST mission itself, the engineers who polished the mirror segments to a fraction of a wavelength of light, the thermal engineers who designed the sunshield to cool the instruments to within 7 degrees of absolute zero, the software engineers who wrote the control systems that deployed 344 mechanisms in the right sequence in the right order in a spacecraft 5 million kilometers from Earth, most of whom will never publish a paper on JADA's GSZ 14.0 or MOMZ14, whose names will not appear in the citation lists of the papers that change cosmology, but without whose work none of this would exist. Science is always this: a chain of human effort stretching backward in time, each link necessary, most of them invisible. The galaxy at the edge of the observable universe was found by Rohan Naidu and his team, but it was found because a woman in the thermal engineering division of Northrop Grumman made a decision about the reflective coating on the 5th layer of the sun shield. It was found because a team at Ball Aerospace spent 3 years polishing a beryllium mirror segment to a tolerance of 6 nanometers root mean square. It was found because a congressional staffer in Washington, in 2011, read a scientist's letter arguing that the telescope should not be cancelled, and was persuaded. The universe has been carrying the light of MOMZ14 for 53 billion years unobserved across the expanding void. It arrived at the detectors of a 6.5 metre gold mirror on April 16, 2025, and was finally seen. The question is not just what we see when we look. The question is what it means that we looked at all. Up to this point, we have been talking about galaxies, individual objects, bright, distant, surprising, chemically anomalous, that challenge specific models of structure formation in the early universe. But there is a larger context into which the JWST discoveries fit, one that extends well beyond the question of how quickly galaxies form, into territory that touches the foundations of physics itself. The lambda CDM model, the standard cosmological model, the framework within which all of the above discoveries are interpreted, is not just a theory about galaxies. It is a theory about the entire observable universe. It describes the composition of the universe in terms of 4 components: ordinary baryonic matter, which makes up roughly 5% of the total energy density, cold dark matter at roughly 27%, dark energy at roughly 68%, and radiation, a negligible fraction in the present-day universe but dominant in the earliest epochs. It describes how those components interact, primarily through gravity, with dark matter and dark energy having no other known interactions with ordinary matter, and how the universe expanded from a hot, dense initial state to its present vast and structured form. This model has been tested in multiple independent ways. The temperature fluctuations in the cosmic microwave background, the afterglow of the Big Bang, mapped with extraordinary precision by the Planck satellite, are perfectly consistent with the lambda CDM predictions to a level of precision that would make most fields of physics envious. The large-scale distribution of galaxies, measured across billions of light-years in surveys like the Sloan Digital Sky Survey, matches the model's predictions for baryon acoustic oscillations and the shape of the matter power spectrum. The abundances of hydrogen, helium, deuterium, and lithium in the early universe, produced in the first 3 minutes after the Big Bang in a process called Big Bang nucleosynthesis, match the lambda CDM predictions with remarkable accuracy. Lambda CDM works. It is one of the most successful quantitative frameworks in the history of science, and it is also, since JWST began operations, under the most serious pressure it has faced since its formulation. The pressure comes from multiple directions simultaneously, which is what makes the current moment genuinely unusual rather than merely another in the long series of anomalies that science regularly encounters and resolves. There is the galaxy number density problem, the 100 times excess of bright galaxies at redshift 14 to 15 revealed by MOMZ14. There is the stellar mass problem. Several galaxies observed by JWST at redshifts above 7 appear to have stellar masses that, under the standard model, should not have had time to accumulate. There is the size and morphology problem. Early galaxies appear in many cases to be more spatially extended and more structurally complex than models predict for objects at those epochs. There is the chemical enrichment problem, exemplified by the oxygen in JDA's GSZ 14-0. And there is the Hubble tension, a pre-existing and deepening discrepancy between 2 independently measured values of the Hubble constant, the number that describes the current rate of cosmic expansion, that is not directly related to the JWST galaxy discoveries, but indicates that the standard model may be missing something at the most fundamental level. The Hubble constant, measured from the cosmic microwave background, from the pattern of sound waves imprinted on the early universe and observed by Planck, gives a value of approximately 67, 4 km per second per megaparsec, measured from Type Ia supernovae and the local distance ladder, a chain of cosmic distance measurements using Cepheid variable stars and other calibrators in the nearby universe. It gives a value of approximately 73 kilometers per second per megaparsec. These two measurements disagree by roughly 10%, and the discrepancy has a statistical significance of more than 5 sigma, meaning, under the assumption that both measurements are correct, the probability that this discrepancy arose by chance is less than 1 in 3 million. The Hubble tension does not directly relate to the formation of early galaxies, but it is a symptom of the same underlying diagnostic. The standard model of cosmology, as formulated in the late 1990s and refined over the subsequent 2 decades, does not fully describe the universe we observe. Somewhere, at some level, something is missing. Something has been misidentified or mischaracterized or left out entirely. What is missing could be something relatively benign, a systematic error in one of the observational calibrations, a subtle effect in the physics of Type Ia supernovae, a small modification to the dark energy equation of state. In that case, the lambda CDM framework would survive intact, with minor corrections, and the JWST galaxy discoveries would be explained by modest modifications to the physics of star formation and feedback in the early universe. Or it could be something more fundamental. It could be that dark matter is not cold, that the dark matter particles have significant thermal velocities that suppress the formation of small-scale structure in ways that the standard model does not capture. It could be that dark energy is not a cosmological constant, not a fixed, unchanging energy density of the vacuum, but a dynamical field that varies with time and space, with properties that were different in the early universe than they are today. It could be that the inflationary episode that is thought to have seeded the density fluctuations from which all structure grew was more complex than the simplest models assume, producing a power spectrum of fluctuations with unusual features at scales that JWST is now probing for the first time. It could, in the most radical scenario, be that some of our most basic assumptions about cosmology require revision, that the universe is not isotropic and homogeneous on the largest scales in the way that lambda CDM assumes, that there is new physics at play in the dark sector, in the 95% of the universe's energy content that we have never directly detected and understand only through its gravitational effects. I want to be clear about something here, because the stakes of this discussion are high enough that intellectual honesty matters more than drama. The JWST observations, as of the middle of 2025, do not prove that lambda CDM is wrong. They demonstrate, robustly, that something in the standard picture of early galaxy formation is incomplete. They raise serious questions about the efficiency of star formation and the properties of stellar populations at high redshift. They put genuine pressure on the model's predictions for the number density and properties of early luminous galaxies, but they do not, by themselves, falsify the framework. A sufficiently clever combination of higher star formation efficiency, a more top-heavy initial mass function, and enhanced feedback suppression can be assembled to match most of the observations at some cost to theoretical elegance, and with some tension with what we observe at lower redshifts. The Hubble tension is a stronger argument for new physics, because it cannot be solved within lambda CDM without violating other well-established measurements. But the solution to the Hubble tension might not be the same solution as the explanation for early galaxy formation. These could be two separate problems with two separate fixes, or they could be symptoms of a single underlying modification to the standard model that resolves both simultaneously. What is not in doubt is the significance of the moment. We are living through the first phase of a systematic exploration of the cosmic frontier, the epoch when the universe first became luminous, when the first stars switched on and drove the reionization of the intergalactic medium, when the seeds of every galaxy, every star, every planet, and every organism that has ever existed were being planted in a universe less than 1 billion years old. And the picture that exploration is revealing is richer, more complex, and more surprising than any prediction that preceded it. The telescope that is doing this exploration was built at a cost of $9.7 billion. Over 24 years, by thousands of engineers, scientists, and technicians working on 3 continents. It was delayed 7 times. It was nearly cancelled once. It flew on Christmas Day 2021 and deployed flawlessly. It is now, with each new observation, extending the catalogue of known objects at the cosmic frontier, probing the physics of the first galaxies, testing the standard model at epochs it was never able to probe before, and finding consistently and reproducibly that the universe is brighter, more structured and more chemically complex at early times than we expected. This is, to my mind, the single most consequential series of observational discoveries of the first quarter of the 21st century. Not because any individual result has definitively broken physics, none has, not yet, but because, collectively, they represent the first time that humanity has been able to look directly at the universe's first chapter. And the universe's first chapter is turning out to be far more eventful than we thought. The stakes of this investigation are not merely scientific. They touch something deeper. They touch the question of whether our picture of cosmic history, the story we tell about where everything came from, how it got here, and where it is going, is fundamentally correct. And right now, for the first time in decades, that question is genuinely open. Science is not a series of triumphs. It is a process of successive approximations, each new result refining, complicating, and occasionally overturning the one before. The JWST discoveries are extraordinary, but they exist within a scientific community that has learned, through long and sometimes painful experience, to be careful about overinterpreting early results from a new instrument, about confusing surprise with revolution, about letting the emotional weight of a dramatic finding outrun the careful quantitative analysis that determines what that finding actually means. So let us spend some time with the complications, because the complications are, in some ways, as illuminating as the discoveries themselves. The first and most important complication is the systematic uncertainty in stellar mass measurements at high redshift. When astronomers report that JDES GSZ 14-0 has a stellar mass of several hundred million solar masses, a number that seems impossibly large for a galaxy existing just 290 million years after the Big Bang, that number is not directly measured. No one is counting stars. The stellar mass is inferred from the observed brightness of the galaxy at multiple wavelengths, combined with a model for the stellar populations and dust properties that produce that brightness, and the connection between observed brightness and underlying stellar mass is model-dependent in ways that are genuinely uncertain at high redshift, specifically the initial mass function. The distribution of stellar masses among newly formed stars affects the inferred stellar mass significantly. A top-heavy IMF, in which a larger fraction of stars are massive, produces more ultraviolet light per unit of total stellar mass than a standard IMF. If early galaxies have a top-heavy IMF, which is plausible for the theoretical reasons discussed earlier, then their actual stellar masses may be lower than estimates based on a standard IMF would suggest. Some analyses have suggested that correcting for a plausible top-heavy IMF could reduce the stellar mass estimates of the most extreme early galaxies by a factor of a few, bringing them closer to the range that standard models can accommodate. This is a real effect, not a convenient hand wave, and it means that the too massive problem, the inference that early galaxies contain more stellar mass than lambda CDM allows, may be, at least in part, a problem with how we infer stellar mass rather than a problem with when that mass formed. The galaxies may not actually be too massive. They may just appear too massive under the assumption of a standard IMF that does not apply at high redshift. However, and this is crucial, the IMF argument does not solve all of the problems simultaneously. It helps with the stellar mass numbers. It does not help with the number density problem. MOMZ14 is too numerous at redshift 1415 by a factor of more than 100, regardless of what you assume about its stellar population. The number density is derived from counting galaxies per unit volume per unit redshift interval, a measurement that does not depend on stellar mass estimates, but only on the brightness and number of confirmed sources in a well-defined survey area. And that number is incompatible with standard models. The second complication is the question of active galactic nuclei. AGN, supermassive black holes at the centers of galaxies that are actively accreting matter and releasing energy, sometimes outshining the entire stellar population of the host galaxy. An AGN can mimic a very luminous young galaxy in photometric surveys, and to some extent in spectroscopic observations as well, because the emission lines produced by the hot gas around an accreting black hole can overlap with the emission lines produced by massive stars in a young stellar population. Webb has, in fact, found an unexpected population of AGN in the early universe. Compact, red-coloured objects that have been whimsically named little red dots by the astronomical community, which appear to be AGN hosted in galaxies at redshifts between 4 and 10, and which are significantly more numerous than pre-Webb models predicted. The existence of this population raises the question of whether some of the bright early galaxies that appear stellar light dominated are actually AGN dominated in disguise, with the AGN contribution boosting their apparent luminosity above what the stellar mass alone would produce. For JADES GSZ 14-0, the AGN explanation has been examined carefully and largely rejected. The key evidence is the spatial extent of the galaxy. It spans 1,600 light-years, which is far larger than any compact AGN emission region would be. An AGN powerful enough to produce the observed UV luminosity from a compact region would produce emission concentrated in a much smaller area than the extended structure observed. The fact that the UV emission is distributed across 1,600 light-years, resolved in Webb's imaging, argues strongly that it comes from a distributed population of stars rather than from a central black hole. For OMZ14, the situation is somewhat different. The galaxy is extremely compact, just 74 parsecs in radius, smaller than even the most compact dwarf galaxies in the modern universe. This compactness does not immediately rule out a stellar-dominated explanation. Compact stellar clusters can be genuinely tiny, but it does make the AGN interpretation harder to dismiss than it is for the more extended JADES GSZ 14-0. The paper by Naidu and colleagues notes that the source is resolve, suggesting an AGN is not the dominant source of light, meaning its spatial extent, while small, is measurably larger than the point spread function of the telescope, which an unresolved AGN would not be. But this is a marginal argument, and it will require more data to settle definitively. There is also the question of gravitational lensing. A foreground galaxy or mass concentration between us and a very high redshift source can act as a gravitational lens, bending and magnifying the source's light. If a bright early galaxy is being magnified by a factor of, say, 5 by an intervening gravitational lens, then its intrinsic luminosity, and therefore its intrinsic stellar mass and star formation rate, is 5 times lower than naive estimates would suggest, potentially bringing it back within the range that standard models can accommodate. JADES GSZ 14-0 has, in fact, a known nearby companion galaxy that provides a mild gravitational lensing boost. The discovery paper notes that the luminosity is mildly boosted by means of gravitational lensing. The exact magnification factor is estimated to be small, but it is present, and it illustrates the general principle that high redshift sources found near foreground structures need to have lensing corrections applied carefully. For MOMZ14, located in the cosmos field away from any obvious massive foreground structure, strong lensing magnification is unlikely, but weak lensing, a gentle, diffuse magnification from the large-scale distribution of matter along the line of sight, is always present at some level for any source at cosmological distances, and its effect on the number density statistics of very high redshift sources requires careful modelling. The third, and perhaps the most technically demanding, complication is the completeness and contamination of the photometric samples from which spectroscopic targets are selected. Webb surveys identify candidate high redshift galaxies through their photometric properties, specifically the fact that they appear in longer wavelength bands and disappear at wavelengths below the Lyman limit, a signature called a Lyman break. But this signature can be mimicked by certain types of galaxies at much lower redshifts. Dusty galaxies with unusual spectral energy distributions, galaxies with extreme emission lines that boost their flux in specific photometric bands, or even stars within our own galaxy with unusual colours. Some of the most confidently selected high redshift photometric candidates from early JWST surveys did turn out, on spectroscopic follow-up, to be lower redshift interlopers. This contamination is a real problem for any statistical analysis of the early galaxy population. If the photometric samples are contaminated at even a modest level, say 10%, the number density estimates derived from those samples could be inflated by a corresponding amount. The MOM survey was designed specifically to address this concern by spectroscopically confirming or rejecting a well-defined homogeneously selected sample, and the confirmation rate and contamination fraction from that survey will be reported in a subsequent paper by the full team. But even after all of these complications are applied, lower stellar masses from a top-heavy IMF, modest lensing corrections, careful treatment of AGN contamination, rigorous photometric selection completeness, the excess of bright galaxies in the early universe does not go away. It is reduced, it is made more uncertain, but it persists. The most honest summary of where the field stands in mid-2025 is this. The standard model of galaxy formation within lambda CDM cosmology predicts the properties of early galaxies with imperfect accuracy, and the imperfection is not random noise, but a systematic bias in a specific direction, toward predicting fewer, fainter, and less chemically enriched galaxies at high redshift than are observed. The magnitude of this discrepancy is large enough, and has been reproduced across enough independent surveys with enough different instruments and analysis methods to constitute a genuine problem that requires a genuine solution. That solution has not yet been found. Several candidates exist. The right answer may involve all of them, or none of them, or some combination of physics that has not yet been fully identified. The cosmic frontier is genuinely open, and this is precisely the kind of situation that makes astronomy, at its best, so remarkable. We have built a machine, an extraordinarily expensive, technically audacious, politically precarious machine that can look further into the universe's past than any instrument that has ever existed. And that machine is looking back and telling us, with growing clarity and growing insistence, that the story we thought we knew is not quite right. The universe has been surprising us for the entirety of the time we have been asking it questions. It is surprising us now. The question of what is wrong with our models, whether it is the physics of star formation, the nature of dark matter, the properties of dark energy, or some combination of all three, will be answered in the coming decade by Webb's continued observations, by follow-up studies with ground-based facilities like ALMA, and the upcoming extremely large telescope, by future space missions like the Roman Space Telescope and Euclid, and by the theoretical and computational work of a generation of cosmologists who are now, for the first time, looking directly at the epoch they have been theorizing about their entire careers. The answers will come. They always do. But first, there is the question of what those answers might mean, not just for galaxy formation, but for the deepest, most ambitious project in the history of human thought, understanding why anything exists at all. We are at the beginning of something. Not the end, not the middle, but the genuine beginning of an era in which the first chapter of cosmic history becomes, for the first time, directly accessible to observation. MO-MZ14 at redshift 14.44 represents the current observational frontier, but it is not the physical frontier. The first stars, population 3 stars, the pristine hydrogen and helium giants that lit up the universe for the first time, are thought to have formed somewhere between 100 and 400 million years after the Big Bang, corresponding to redshifts roughly between 15 and 30. Above redshift 14, the intergalactic medium was almost entirely neutral, and the Lyman alpha emission from galaxies was largely absorbed before it could travel any significant distance. This makes the detection of galaxies at redshifts above 15 or 16 extraordinarily difficult. The very opacity of the early universe works against us, blocking the spectroscopic signatures that allow us to confirm distances, not impossible. Webb's NIRSpec prism can, in principle, detect the Lyman break signature, the abrupt disappearance of flux shortward of the Lyman limit, at redshifts up to roughly 20 or beyond, even in the absence of emission lines. The photons that constitute the continuum flux of a galaxy above redshift 15 are stretched into the mid-infrared by the time they reach us, and Webb's NIRCam and MIRI instruments, working together, can in principle detect them. The challenge is sensitivity. Galaxies at redshifts above 15 are expected to be, under any plausible model, genuinely fainter than the objects Webb has confirmed so far, and detecting them will require either significantly longer exposure times or the assistance of gravitational lensing magnification from foreground galaxy clusters. Some photometric candidates at redshifts above 16 have already been reported in the literature, tantalizing hints, each requiring careful spectroscopic follow-up to confirm or refute. One candidate, identified in early deep field imaging, has a photometric redshift estimate above 18, which would place it at roughly 180 million years after the Big Bang if confirmed. Whether such objects will ever be spectroscopically confirmed remains to be seen. The photometric evidence is preliminary. The contamination from lower redshift interlopers is significant at these extreme distances, and the sensitivity requirements for spectroscopic confirmation push against the practical limits of what Webb can achieve. The next major advance at the cosmic frontier will likely come from the combination of two tools, the Roman Space Telescope and the Extremely Large Telescope. Nancy Grace Roman Space Telescope, expected to launch in the late 2020s, will survey areas of sky roughly 100 times larger than Webb's deepest fields, with a wide-field near-infrared camera that will identify thousands of high redshift galaxy candidates across thousands of square degrees. These candidates can then be followed up spectroscopically with Webb in the near-infrared, and with the Extremely Large Telescope, a 39-metre ground-based telescope under construction in the Atacama Desert, at optical and near-infrared wavelengths with exquisite spectral resolution. This combination, wide-field photometric discovery from Roman, detailed spectroscopic characterization from ELT and Webb, is the strategy that will systematically map the galaxy population from redshift 10 to the cosmic frontier at redshift 20 and beyond, with enough statistical power to move from individual record-breaking discoveries to population-level statistics that can truly discriminate between competing models of early galaxy formation. In parallel, ALMA will continue to play a decisive role. The detection of heavy element emission lines, oxygen, carbon, nitrogen, in high redshift galaxies through their far infrared emission is one of the most powerful tools available for measuring chemical enrichment, star formation rates, and gas dynamics in the early universe. The ALMA detection of oxygen in JADES GSZ 14-0 demonstrated that this tool works at redshift 14. In principle, with sufficient integration time and optimal atmospheric conditions at the Atacama Plateau, ALMA could detect similar signatures in even more distant sources, probing the chemical enrichment of the universe at redshifts approaching 15 or beyond. The science that these observations will enable goes far beyond the discovery of progressively more distant individual galaxies. It encompasses the reionization history of the universe. The process by which the neutral hydrogen that permeated the cosmos after recombination was gradually ionized by the radiation from the first stars and galaxies, a process that was substantially complete by about 1 billion years after the Big Bang, but whose detailed history, which sources contributed most, over what timescale, with what spatial structure, is still poorly understood. Webb's observations are already beginning to map the topology of reionization, identifying regions of the early universe where the intergalactic hydrogen was already partially ionized earlier than expected, and probing the relationship between the most luminous early galaxies and the ionization state of their surrounding medium. MOMZ14 itself provides a hint here. The paper notes that the absence of a strong damping wing may indicate that the immediate surroundings of MOMZ14 are partially ionized at a redshift, where virtually every reionization model predicts a approximately equals 100% neutral fraction. This is a remarkable statement. At redshift 1444, almost every model of cosmic reionization expects the intergalactic medium to be essentially completely neutral, opaque to Lyman alpha photons, unseen as a void of neutral hydrogen stretching in all directions from any luminous source. And yet the spectrum of MOMZ14 shows no sign of the complete Lyman alpha absorption expected from this neutral medium. Something has already ionized the gas around this galaxy, presumably the galaxy itself, through the radiation from its intense burst of star formation. The tenfold increase in star formation rate detected in the past 5 million years of its observed life has carved out a bubble of ionized gas around it, a region of transparency in an otherwise opaque universe. This is the first direct evidence of reionization at redshift 14. A single galaxy, compact and brilliant, burning so intensely that it has already altered the state of the intergalactic medium around it, already begun the process that will, over the next billion years, transform the entire universe from a sea of neutral hydrogen to the largely ionized medium we inhabit today. The implications for the timeline of cosmic reionization are significant. If galaxies like MOMZ14, far more numerous than standard models predicted, were already driving local reionization at redshift 14, then reionization may have begun earlier, proceeded more rapidly in some regions, and been a more spatially inhomogeneous process than the smooth, late-starting scenario that many models assume. The full reionization history of the universe, the detailed record of when each cubic megaparsec of intergalactic space transitioned from neutral to ionized, is one of the grand outstanding problems in observational cosmology, and JWST, combined with radio observations from facilities like the Square Kilometre Array, now under construction in South Africa and Australia, is beginning to supply the observations needed to solve it. There is also the question of what happens to galaxies like MOMGD14 and JADA's GSGD14-0 as the universe continues to evolve. Are they the progenitors of specific types of galaxies we see in the modern universe? Are they the seeds of massive ellipticals, the giant, red, largely dead galaxies that populate the cores of modern galaxy clusters, which appear to have formed the bulk of their stars very early and then stopped? Are they the progenitors of galaxies like the Milky Way? Or are they fundamentally transient structures, intense bursts of star formation that will be disrupted, merged, and absorbed into larger systems over the next several billion years, leaving no direct surviving descendants? The globular cluster connection, if confirmed, provides one possible answer. Some of the stars forming in these early galaxies may survive as globular clusters, orbiting the outskirts of much larger merged systems, preserving the chemical signatures of their birth environment for 13 billion years. This would mean that, in studying the globular clusters of the Milky Way and Andromeda and Centaurus A and every other nearby galaxy, we are already studying the stellar products of the first era of galaxy formation, not indirectly, through models and simulations, but directly with every telescope that has ever observed a globular cluster star. This is the kind of connection that, when it is fully established and fully understood, will represent one of the great conceptual bridges in the history of science. The bridge between stellar astrophysics and cosmology, between the study of the oldest stars in our cosmic neighbourhood and the study of the most distant objects ever observed by human instruments. The bridge is not yet complete. It rests on a 3 sigma detection and a compelling theoretical framework and a great deal of circumstantial evidence. But it is being built by a generation of astronomers who grew up watching Hubble images on the internet and are now writing the papers that will define the next 50 years of cosmology. And the telescope that is enabling all of this, sitting at L2, 1.5 million kilometers from Earth, cooling its instruments to 7 degrees above absolute zero, collecting infrared photons that have been travelling through expanding space since before our solar system existed, that telescope has enough fuel, by current estimates, to operate for at least 20 years. The era of cosmic frontier science has barely begun. On a clear night in the Atacama Desert, 5,000 metres above sea level, the sky does something that is hard to describe to someone who has never seen it. At that altitude, with the atmosphere so thin that you can feel its absence in the effort of each breath, the stars do not twinkle. They are steady, hard and cold and perfectly still, like holes in a dark cloth through which something else, something older and stranger, is shining through. The Milky Way is not a smear or a suggestion, it is a structure. A river of light with depth and texture, dense in some places and transparent in others, full of dark lanes and bright nodes, that, if you have spent any time at all learning what you are looking at, resolve themselves in your mind into star-forming regions and dust clouds and stellar nurseries and, in the direction of Sagittarius, the dense, churning, magnificent core of the galaxy itself, somewhere in the direction of the constellation Fornax, low in the southern sky on autumn nights, an unremarkable patch of sky containing no bright stars, no distinctive shape, nothing that would cause a casual observer to pause. There is a galaxy that existed 290 million years after the Big Bang. You cannot see it with the naked eye. You cannot see it with binoculars. You cannot see it with the best amateur telescope on Earth. Its light is so faint and so thoroughly redshifted into the infrared that no human eye could ever detect it under any conditions. It exists in the universe's database, retrieved only by machines built to that specific purpose, stored in digital files on servers, accessible only through spectra and models, and the practiced mathematical translation of photons into physics. And yet it is there, was always there. For 13.4 billion years, the light from that galaxy, the light of hundreds of millions of stars burning in the first 290 million years of cosmic history, stars that have since been dead for longer than the Earth has existed, has been travelling through the expanding universe, its wavelength stretching as the space it crosses grows. It crossed the void between the first galaxies, from a time when the universe was dense and hot and full of the noise of reionization. It crossed the long, dark middle period when the universe was transparent but quiet, when galaxies were assembling and dark matter halos were merging, and stars were living and dying in the billions. It crossed the era of quasars and galaxy clusters and cosmic web. It crossed the last billion years of accelerating expansion, when dark energy began to pull the universe apart at a rate that will eventually separate every galaxy from every other galaxy until each one exists in a dark and empty island universe with no visible neighbours. And it arrived on April 16, 2025 at the detectors of an infrared spectrograph on a telescope, orbiting a star in an unremarkable arm of an unremarkable spiral galaxy, and was caught. That it was caught at all is a fact worth sitting with for longer than we usually do. The universe has been running its physics for 13.8 billion years without any witness. The Big Bang happened in the absence of observation. The first stars ignited in darkness. The first galaxies assembled, burned, and began to enrich the cosmos with heavy elements across billions of years, during which there was no one to watch, no instrument to record, no mind to wonder at what was happening. The universe did not need our attention to proceed. It does not need our attention now. It will continue to expand and cool, and eventually, in 1 trillion years or so, approach a state of maximum entropy, stars extinguished, black holes evaporated, everything spread thin and cold and motionless, with or without anyone watching. And yet we watch. We build machines at a cost of $9, $7 billion, and launch them on Christmas morning into the cold between worlds and cool them to 7 degrees above absolute zero, and point them at patches of sky so small you could cover them with a grain of sand at arm's length. And we collect the photons that have been in transit since before our planet existed, and we turn those photons into numbers, and those numbers into spectra, and those spectra into knowledge, and we say, here, this is what was here. This is what was happening when the universe was just 280 million years old. The knowledge we extract from this process is incomplete. The models are wrong in ways we are only beginning to understand. The three biggest questions: how did galaxies form so fast? What is dark matter? And what is dark energy? Remain as open as they were before Webb flew, even as the telescope makes them sharper and more specific. We have not solved the universe. We have only seen more of it, and found that what we see is stranger and richer and more difficult than we expected. And maybe that is the point. Not to arrive at answers, but to sharpen the questions to the point where the answers become possible. The generation of astronomers who built the theoretical models that JWST is now straining did not fail. They made predictions precise enough to be tested, which is one of the highest achievements in science. The generation of engineers who built Webb did not merely build a telescope. They built the instrument by which the next chapter of cosmology will be written. The generation of astronomers who are right now, in 2025, analysing Webb spectra and ALMA data and writing the papers that describe MOMZ14 and JDES GSZ14-0 and dozens of galaxies not yet discovered. They are not ending a story. They are opening one. There is a galaxy at redshift 20 that no one has yet confirmed. There may be galaxies at redshift 25. There are, almost certainly, stars forming at epochs we have not yet probed, in conditions we have not yet characterized, with properties that will surprise us at least as thoroughly as MOMZ14 surprised Rohan Naidu when its spectrum came in on the 16th of April. There is an explanation for why the universe at redshift 14 looks the way it does, an explanation that is consistent with everything we know about physics and cosmology. And somewhere, in a graduate student's notebook or a theorist's simulation code, or a future telescope's as yet unwritten observing program, that explanation exists, waiting to be found. We are the generation that looked, the generation that built the machine, the generation that first read the light of the universe's first chapter, first decoded the oxygen in a galaxy that existed before the sun's star-forming cloud had coalesced, first counted the galaxies at the edge of everything, and found that there were more of them than the equations expected. We are also, inevitably, the generation that will be wrong about some of this. Models will be revised. Some interpretations will not survive. The nitrogen to carbon ratio in MOMZ14 will either be confirmed or will dissolve into noise. The stellar mass estimates will be refined and will change. New surveys will discover galaxies at redshifts of 15 and 16 and possibly beyond. Galaxies whose properties will either confirm the emerging picture or complicate it further, as the universe has a way of doing. The Hubble tension may be resolved by new physics or by a new calibration. The next generation of cosmological simulations, trained on the JWST data, will produce a new standard model, not lambda CDM exactly, but something more precise, more nuanced, more capable of matching what we observe. This is what knowledge looks like when it is being built, as opposed to when it is being reported after the fact. It is messy and uncertain and full of blind alleys and partial answers and provisional conclusions that may not survive contact with the next observation. It is also, for those willing to sit with it in its unfinished state, one of the most exhilarating things that human beings do. That smudge of pixels in a data file on a server in Baltimore. Those few hundred photons caught by a 6.5-meter mirror coated in 700 atoms of gold orbiting at the gravitational balance point between the Earth and the void. Those photons are the most distant messengers that any mind has ever received. They carry, encoded in their wavelengths and intensities, the story of a universe that was already busier, already more complex, already more surprising than anything we predicted. They have been in transit for 13.53 billion years. We got here just in time to catch them. The question they carry is still open, and the universe, as always, is not waiting for us to close it.